Hi everyone. We're going to try something new for class this week. I'm hoping that everybody is watching this before they get to class because this time I'm going to go over the explanations in this short video, and when you get to class we can start practicing right away, and then I can help you with your understanding and check your problems that you're working on and work more one-on-one with you guys than I maybe did first semester. So here's to hoping that you guys are viewing this and that the recording is going well. If there's anything confusing in the recording, make sure you let me know when you come to class. All right, but in 6.03, we are going to go over graphing systems of linear equations. So in 6.01 and 6.02, we talked that a system of equations are all graphed on the same coordinate plane, and we look for where our lines will intersect each other. We talked about how to solve linear equations, so a system of linear equations, algebraically by using substitution and the elimination method. And then we talked about some nonlinear equations and how to find their solutions. Today we're going to go back to graphing systems of linear equations and talk about that. So don't forget, for graphing, we do have steps that we follow, and they are, so to graph, we want to make sure our equations are written in slope-intercept form. Okay? So slope-intercept form is that y equals mx plus b. So basically you want to isolate your y variable. So you want to manipulate your equation so that you can solve for y. Once you have your equations in slope-intercept form, you can pull the important information, which is what is your slope and what is your y-intercept. Once you have that information, we can go ahead and start to graph. So we start by graphing the y-intercept, and then we use our slope to help us find additional points on our lines. And then lastly, we connect those points to form our line. So those are the four main steps that we have for graphing on a coordinate plane. All right, don't forget that just like when we solved it algebraically with the elimination method and the substitution method, there were special cases. So your special cases are if your lines are parallel. Right? So if you have parallel lines, there is no solution. Also, if you have the same line, there are infinitely many solutions. Okay. How do I know whether I have parallel lines or whether I have the same line? Remember, parallel lines, your equations have the same slope, but different y-intercepts. So if you see that occurring, that is your indicator that you have parallel lines. So when you pull that important information from step 2, and you notice that the slopes are the same and your y-intercepts are the same, do you even need to go and graph it? Technically, no, right? Because you know that they're going to be parallel lines. So, and you know that parallel lines will never intersect. Therefore, there is no solution. Now, the exact opposite of that, if it's the same line or coincidental lines, that means there's infinitely many solutions. And that means that we have the same slope and the same y-intercept. So these lines are identical. They're going to fall right on top of each other. And that is why there's infinitely many solutions, which means you can take any point on that line and it's going to work in both of your equations. All right, there are times when you may have to break equations apart. So here it doesn't look like there are actually two equations present because you have 6x minus 12 equals negative 4x plus y, and you only see one variable represented in that problem. However, we can use kind of the substitution method in reverse here. So what we can say is we can say, well, y will equal 6x minus 12. And y can also equal negative 4x plus 8. So kind of seeing that substitution method in reverse here, because here, if I were to substitute this equation into the other or vice versa, we end up with what we have up here. So you can break those apart into two separate equations. And we could go ahead and graph from here as well. So if I wanted to graph this first line, 6x minus 12, I know that it's already in slope-intercept form. So my slope is 6. My y-intercept is negative 12. So I'm going to start right there. I'm going to move up 6 and 1 to the right. And I'm going to do that a couple of times before I actually connect those points because I want to get a pretty accurate graph here. The more accurate it is, the better that you're going to find that intersection point. Okay. For the second equation, we're going to use the slope of negative 4 and the y-intercept of positive 8. So I start at positive 8 and I move down 4 and to the right 1. And I can keep doing that. And I think I might have been. Yep, I'm off 1. I want to be 1 lower here. Like that didn't look quite right. Okay, and you can do that a couple of times and you'll get that good representation and you can see that intersection a little bit more clearly there. So our solution for this problem is where they intersect, which is at positive 2, 0. And if you wanted to, you could go ahead and substitute those values into both equations and you should get true statements each time. Don't forget that we can also use graphing technology to help us find intersections. So in the live class, I will bring up the graphing calculator for you for some problems, or you can go ahead and use GeoGebra.com as well. Or .org, I apologize. All right, so let's just look at one example together here. And it says, Elizabeth is working in the concession stand during a basketball game. Each hot dog sells for $3 and a soda is $2. At the end of the first half, Elizabeth sold 23 items and made $59. How many hot dogs did she sell? All right, so we actually need to create our system and then go ahead and plot it or graph it and see where our two lines intersect. So I'm going to let hot dogs be represented with the variable x, and soda is going to be my variable y. So I know I'm selling hot dogs and sodas, and I sold 23 of those items. Now my second equation is going to come from the cost. So if hot dogs were $3 each, that's going to be 3x, and a soda was $2 each, that's 2y, and I know I made $59. All right, so I want to go ahead and graph each of those. Before I do that, though, it would probably be wise to solve for y. So if you're going to use the graphing calculator that's in the classroom here, you're going to have to solve for y. Or if you're going to use GeoGebra, you don't technically have to solve for y, but it might be a good practice just to get used to that. I'm going to go ahead and hopefully you guys can see GeoGebra pop up here in your screen. But I'm going to just go ahead and type in 3x plus 2y equals 59 for us. So it's way off to the right-hand side of our screen. And my other one was x plus y equals 23. And you can see that it doesn't really look like it's intersecting at all, but we can move our graph up here, and we do see that the lines are intersecting, so the solution is going to be right there. I'm going to use the more accurate approach, and I'm going to find the actual intersection of those two lines. So we'll find the intersection of line A and the intersection of line B, and we notice that it intersects at the point 1310. So what does that mean? What does 1310 mean for our solution? So if I come back here, I got the point 1310. But remember, our points are always labeled X, Y. So X represented the hot dogs. So she sold 13 hot dogs and she sold 10 sodas. All right, so when you come to class, that was a good overview of how to graph and find solutions for our systems of equations there. So when you come to class, we're still going to start with announcements at the beginning, but then I'm going to send you right into breakout rooms as soon as those are done so that you can begin working on problems. I, of course, will be coming around to the breakout rooms to check your understanding throughout the class. And if any questions arise as you're working through things, obviously raise your hand to let me know. All right, thanks for watching this recording, and I will see you guys in the live class. Bye, everyone.